Is it on? I didn't hear it go. Bleh.
It did.
But the clock is ticking?
Yeah.
Okay, great. Okay, you guys, hey, what are we going to learn today? Very simple. We're going to talk about infinite series. That is when you have an infinite number of numbers that you're adding together, an infinite series. We're going to talk about one special type of infinite series called geometric series. Then we're going to talk about an infinite polynomial, not an infinite just series of numbers that you're adding, but a polynomial with an infinite number of terms and thus an infinite degree. Is it a fourth degree? Is it a 12th degree? No, it's an infinite degree because it's got an infinite number of terms and the highest exponent on this power series will be infinity. And then finally, we will combine them and learn about a special type of power series, a special type of polynomial that's not a Taylor polynomial, it's not a Maclaurin polynomial. Rather, it's called a geometric power series. So this is going to be our second approximating polynomial. And it won't be Taylor or Maclaurin, it'll be a geometric power series. But it's still an approximating polynomial. It's a polynomial equation that approximates a function, a weird function. So let's get started. First, infinite series. Okay? An infinite series is a bunch of numbers that you add up, an infinite number of numbers. These infinite series sometimes converge. And when I say an infinite series converges, that means it adds up to a finite number. Adds up to a finite number. Okay, so like here's an example, the classic example, 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... forever and ever and ever. So this is an infinite series. You're adding an infinite number of numbers, plus a 32nd, plus a 64th, plus 1/128th, plus blah, 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 forever and ever. And yet, even though I'm adding up an infinite number of terms, do you know what this series actually adds up to? Yes, Daniel?
1.
Yeah, it adds up to 1, right? And you get that classic, story about Achilles and the hare. I don't know if your teacher ever told you about that, where Achilles is chasing after a bunny rabbit, a hare, and with every moment or every step or every minute or whatever, he's cutting the distance between him and the hare in half. Right? Every minute, we'll call it every minute he cuts the distance between him and the hare in half. Will he ever catch the hare? Yeah, and it depends how you look at it. Yeah, you might say, no, he'll never actually get there. Or you might say, well, no, if you give him an infinite number of minutes, he will actually get there. And it depends how you look at it. And of course, you'll get so close to the hare that you can actually reach out and grab him anyway. But the point is, yeah, that's a converging series. Okay? Sometimes they diverge. And when a series diverges, that means it doesn't add up to any particular number, or it adds up to infinity. Doesn't add to a particular number, or adds to infinity. So of course, one series that diverges would be 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus ... right? If you're going to add an infinite number of 2's, what do you get?
Infinity.
Yeah, infinity. So this guy diverges. It doesn't add to a particular number, it adds to infinity. And any number that you say it adds to, you just add 2 to it, and now it doesn't add to it anything. You see? Another one would be this, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus ... What's this guy add up to?
0. Or actually,
0 or
1.
or 1, depending on when you stop, right? If I stop here, it adds to 0, but if I add one more term, it adds to 1. So it doesn't add to any particular number. So we'd still say it diverges, because it doesn't add to any particular number. Here's another one that's a little trickier. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... You might think, since the terms are getting smaller and smaller, that it's reminiscent of this. But actually, this guy adds to infinity. If you were to get your graphing calculator and add a 5th plus a 6th plus a 7th plus an 8th and just keep going, with each number you add, your total just gets bigger and bigger. And there's no limit to it. It would just get bigger and bigger and bigger. And if you added an infinite number of terms, you'd get infinity. And like I said, you can try it on your calculator if you like. Well, we're going to be investigating this in earnest in a few days, where we're going to look at just tons and tons of infinite series and determine if they converge or diverge. But the first type of infinite series we're going to deal with, the one we're going to deal with today, is this special type of infinite series. And tell me, do you notice what the rule is? Like, how do you get the next term knowing what the previous term is? What are you doing? Say it again? Say it again?
You multiply the denominator by 2.
Yeah, multiply each denominator by 2. Or multiply the entire number by 1/2. Are you okay that that's how you get the next term? And there's a special name for the type of series where each term is a certain number multiplied by the previous term. It's called a geometric series. The simplest infinite series. The simplest infinite series. Whoops. I didn't mean to write the word infinite because I put this, well, I guess it's too late now. Simplest infinite series is the geometric series. That's the series, the sum equals the sum as n goes from 1 to infinity of a r to the n minus 1 power. So hey, let me practice this with you just a little bit. What if I gave you the sum as n goes from 1 to infinity of 2 times 3 to the n minus 1 power? Could you write out the first 3 terms? Go ahead and do that now. What are the first 3 terms of this infinite series? I need to make sure you can do this, that you can deal with sigma notation. Okay. Hopefully you're plugging 1, 2, and 3 in for n, because n goes from 1 to infinity. So when I stick 1 in, this is 3 to the 0 power, which is 1. So this first term is 2. When I stick in a 2, I get 2 times 3, which is 6. When I stick in a 3, I get 2 times 9, which is 18. You'll notice each successive term is being multiplied by 3, right? That's the significance of r. How many people got 2, 6, 18? Okay, so how many people have had experience with sigma notation? Okay, good for you guys. Then also this r, there's a name for r. It's called the common ratio. It's called the common, oops. It's called the common ratio because this R is always the ratio of a term and its preceding term. So the ratio of 6 to 2 is 3. The ratio of 18 to 6 is 3. So 3 is the common ratio. Here, how about this guy? N goes from 1 to infinity of 4 times, or here, let's make it 12. 12 times negative 2/3 to the n power. Go ahead and write out the first 3 terms of that guy. I want to see if you can get, oh, whoops, 3 to the n minus 1 we'll go with, so that your first term is 12. Stick in a 1, I get 12. Stick in a 2. Okay. I hope everyone's getting for the second term that the second term is going to be negative. Because when I stick a 2 for n, 2 minus 1 is 1, and negative 2/3 of the first power is negative 2/3. So this guy ends up being negative 8. And then stick in a 3, I got 4 9ths. And so I got 48 9ths. Right, which is 5 in the third. Well, or you can call it 16/3. Anyone calling it 16/3? Ah, that's fine. I'll go 16/3. Because it's easier to deal with. Okay? The point is, you'll notice when your R is negative, you end up with what's called an alternating series. And we'll talk about that more like in a week or so. This idea that the terms alternate positive, negative, negative. Okay? Well, is this series going to converge or diverge? Yeah, it's diverge, right? They're getting bigger and bigger and bigger. Okay? But look at this series. Do you see how the terms are getting smaller and smaller? How the next term would be, what is that, 32 over 9, and then the next term would be 64 over, 327, etc. Do you see how the terms are getting smaller and smaller and smaller? Is this guy going to converge or diverge? Yeah, it ends up converging. Because geometric series converge. And now you may have learned this already. What has to be true about R for a geometric series to converge? Not negative, yes?
It must be constant.
Okay, well, no, because here it's constant. R is constant, it's 3. But this is obviously diverging. And being negative isn't good enough because I can give you a geometric series where R is negative, right? But that's going to diverge. Right, this is, 1 minus 2 plus 4 minus 8 plus 16 minus 32 plus 64. Pretty soon, each term you add is going to be just banging back and forth between positive and negative infinity. So this guy's going to diverge. So being negative isn't going to make something diverge. Yes, Abigail?
I mean, between negative and positive one?
Yeah. How did you know?
The example you gave there, the common ratio was 1/2, and the
Yes.
common ratio is 2/3, is what the limit between.
Yeah, good for you. Good deductive reasoning. Yeah, so, and that ends up being true. And I'm not going to go through the proof of it, just because I'm kind of running short on time, but I just want to let you know that geometric series converge when R is between negative 1 and 1.
Plus,
And I'm embarrassed not to show you why to the video audience, but what can you do? Geometric series converge when R is between negative 1 and positive 1. Or another way to write this is when the absolute value of R is less than 1. Okay? Why won't a geometric series converge when R is 1? Why won't it converge under those circumstances? Like if I had this, 3 times 1 to the n minus 1 as n goes from 1 to infinity. Why doesn't that guy converge?
Because it gets infinitely bigger.
Good. Yeah, what's the first 3 terms?
3 plus 3 plus 3.
Yeah, thanks, Daniel. Yeah, 3 plus 3 plus 3. So this isn't going to converge, not if you're just adding 3's forever and ever. You know what I mean? So yeah, r equaling 1, you're not going to get convergence. How about negative 1? Maybe that's an exception.
It's going to go to negative.
No, it won't go to negative infinity.
0.
Because what's the first 3 terms, or the first 4 terms? What's the first several terms going to be?
3 minus 3.
Yeah. 3 minus 3 plus 3 minus 3 plus 3. 3 minus 3 plus 3 minus 3 plus 3. So again, this diverges because I've got one of these guys, you know, that doesn't add up to a particular number. It's either 0 or negative 3, or 0 or positive 3, and what it is depends on when you stop. So I hope you guys get that geometric series is going to converge when r is less than 1. And now I'm going to show you what it converges to. And again, I'm doing it without proof. So sorry, video audience. But an infinite geometric series where negative 1 is less than r, which is less than 1, converges as follows. The sum as n goes from 1 to infinity of a r to the n minus 1 power equals a over 1 minus r for negative 1 being less than r, which is less than 1. So that's the handy dandy formula you plug into. Just a over 1 minus r. So for example, this first guy we did, okay, what's the first term? Half. What's my r? Half. So what's the sum? 1. You see? So, hey, let's do another one. The one we already did, n equals 1 to infinity of 12 times negative 2/3 to the n minus 1 power. I'd like everyone to please get the first term, get the common ratio, and plug into that formula. And let's see what this guy here, what this guy actually converges to. Alrighty, the first term, are you guys getting it? It's 12. Okay, and the common ratio is negative 2/3. So I got 1 minus negative 2/3, which is the same as 12 over 5/3, which is the same as 12 times 3/5, which is 36/5, right? Am I getting that right?
Yeah.
Yeah. Thank you. All right, which is 7 1/5. So that's what that crazy guy converges to, 7 1/5.
Wait, Mr. Shin?
Yes.
So you just take the first term? Oh, I thought you took A.
No, you got to make sure that your first term is A. So it'll require you to plug in. Okay. Now, before I go on, there's an alternate way to write this. I don't have to write it like this with n minus 1. I'm just doing this because this is the way you supposedly learned in Algebra 2. Did you guys do sequences and series in Algebra 2? Okay, in your textbook, if I think I'm not mistaken, you guys always start with n equal 1. But what's going to happen is here in calculus land, sometimes you'll start with n equal 1 and sometimes you'll start with n equals 0. So sometimes you'll get this guy expressed as follows. N goes from 0 to infinity as 12 times negative 2/3 to the 0 power. Oops. Negative 2/3 to the n power. And so you tell me, what's my first term now?
12.
Yeah, still 12. This is the same as that. It's just instead of starting at 1, I start at 0, and instead of having n minus 1 power, I have n power. But this guy is identical to that. And so in this, unfortunately, in calculus land, you're kind of going to be asked to be able to deal with both scenarios, you know? Okay, well, hey, that's it for geometric series. That's it for what you learned in Algebra 2. Now it's time to say what a power series is. And all I'm doing is just telling you, hey, this is a power series. And then we'll learn about geometric power series and interval of convergence. Okay. Power series. Okay. It's just a thing, okay? It's an infinite polynomial. A generic infinite polynomial. Any infinite polynomial someone gives you that is a polynomial with an infinite number of terms, that's going to be called a power series. A polynomial with integer coefficients. I'm sorry, integer exponents, integer exponents. So there's two forms. If I have a power series centered at 0, then the power series is going to be the sum as that goes from 0 to infinity of a to the n, x to the n. That is, it'll be a0 plus a1x plus a2x squared plus a3x to the third plus dot 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 plus a to the n, x to the n plus dot dot dot. And it just keeps going on forever and ever and ever. It's just a polynomial with an infinite number of terms. And each coefficient gets its own name, you know, depending on what term it's in. So that's a power series. Now what's going to happen again in a week or whatever, we're going to start assigning values to A0, A1, A2, A3, and it ends up getting really interesting. But for now, the generic form of a power series looks like that. And if your power series is centered at x equals c, then it becomes like this. A to the n times x minus c to the n. Where every term is no longer x, now it's x minus c, so that when you stick c in, all the terms with x's in them go to 0. So this would be a0 plus a1 times x minus c plus a2 times x minus c squared plus dot 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 plus a sub n times x minus c to the n plus dot dot dot. It's just an infinite polynomial, but we call it a power series. Now comes the whole point of today, which is to teach you what a geometric power series is. Here it comes, the geometric power series. Okay? Geometric power series. All right? And this is not going to, I know this is going to be really strange and foreign to you, but it's not going to require a lot of intelligence on your part. This is another one of those scenarios where you're just mindlessly plugging in, you know? If you've got you get a geometric power series in the special situation where f of x, my weird function, ends up equaling some constant over 1 minus some function of x. If I have a weird function that looks like that, then just as if I have this, it becomes this guy. Or, let me see, or do you mind if I rewrite that? Instead of doing, here I'm going to put this in parentheses. Okay, a over 1 minus r is the sum as n goes from 0 to infinity of a r to the n power. Okay, this is geometric series. A geometric power series just says, hey, instead of r, I'm going to substitute h of x. So a over 1 minus x ends up being this infinite power series from n equals 0 to infinity of a times h of x to the n power. Hey, here comes an example. Because actually the teaching part is done. That's all there is. Here comes number 1. Write f of x equals 3 over 1 minus x as a power series. So this is one I'd call a weird function. It's going to be like a hyperbola-looking thing with its vertical asymptote at x equal 1. But I'm going to express this as a power series. Here it comes. Since a over 1 minus r is equal to this infinite geometric series, 3 over 1 minus x is going to be the sum as n goes from 0 to infinity of 3 times x to the n. Which, if I wanted to rewrite that, it'd be 3 plus 3x plus 3x squared plus 3x to the third plus dot 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 forever and ever and ever. Here, let me do this thing. Let me get this. I gotta unplug this. Put this in. Come on, stupid thing. Just something here. Okay, cool. So I got, what, 3 divided by 1 minus x, okay? And let me see, zoom standard, what does that look like? So I got a kind of a hyperbola looking thing, and this vertical, this actually is nothing, it's them connecting that dot with that dot, which is a really big failing in this graphing calculator. But there's really no good way to get rid of it. I mean, I can do this, but you know, then you have to kind of picture connecting the dots in your head. So I'm just going to have to go with this. Alrighty, and now I'm going to graph the power series, which is 3 plus 3x plus 3x squared plus 3x to the third plus 3x to the fourth. Okay, and I could go on and on and on forever, but hopefully this is enough terms so that this guy looks like that hyperbola. And here we go. Okay, so let's go from like -3 to 0. Here's my hyperbola, and here's my third order approximation, or fourth order approximation. So you see, it's really good, you know, from like, what is that, -3/4 to 0, okay? Here, let's go to like 0.9, because I just don't want to see that stupid asymptote. And so here's the other guy. And so you notice my approximation is good from like -3/4 to positive 1/2 or thereabouts, okay? Alrighty. So are you guys okay with this being an approximation?
Yeah.
Okay, I need to give you guys one more to do on your own, and then I got to talk about interval of convergence, then we'll be done. Okay. Here, do this. Let's say f of x equals 2 over 1 minus x squared. I'd like you to get the first 3 terms and the general term of the power series. And you're going to utilize the geometric power series. You're just going to mindlessly go, oh, this gets me that. So please do that now. I hope everyone's getting their general term to look like this. All you have to do is just whatever your A is, it goes there, and whatever your H of X is, it goes there. So this ends up being 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th plus dot, dot, dot. Hey, by show of hands, how many people got that? Okay, hey, that's all there is to this. That's the beauty of geometric power series. Now, there's something else I need to teach you guys, and that's interval of convergence. But we're not going to get to that today. So what's going to happen is, on every problem where they ask for interval of convergence, just ignore. Just ignore that, and just get me the series. Okay, good luck, you guys. Thank you. Thank you, Paul. Yeah.